Okay, welcome to chapter 20. It's late in the day, and most of you won't be able to get to watch this, so I apologize for that, but here we go. Chapter 20, talking about the Earth, and the Earth is changing all the time. I'm not talking about the living things on the Earth, but the planet itself is changing constantly, but very slowly. The time scale, geologic time scale, is way beyond our human perception, because, you know, if you're lucky, you're going to live to be 100 years, and 100 years isn't even a drop in the bucket of time. It's not even a little second on the clock. So 100 years is nothing. So when we talk about changes in the Earth and how it's changing over time, we're talking long periods of time. Thousands of years, tens of thousands of years, hundreds of thousands of years, millions of years, tens of millions of years, hundreds of millions of years, billions of years. Okay, so we're looking briefly at the Earth over the last 4 billion years or so. But what we think is that there's this idea that things happening today are pretty much how things were happening in the past, and that there's this idea of uniformitarianism, that the processes that are going on now, like erosion and building up of mountains, that it's the same basic rate as times past. So, and this was an important idea for Darwin. He had a book with him that he took on his voyage of the Beagle from Charles Lyell about geology, and this idea of changes, small changes happening over very long time periods in the Earth, that, you know, clicked with Darwin, and he thought about how those processes could lead to changes in living things as well. Okay, so okay, this table here, this geologic scale, is going to be quite important, and there are eons, there are eras, there are periods, there are epochs. Mostly pay attention to these eras and the periods, and let's first focus on the eras: Precambrian, Paleozoic, Mesozoic, Cenozoic. Okay, and each of the eras is divided up into periods, and it would be good for you to know the periods as well, especially maybe not the periods of the Precambrian, because we're just going to lump the Precambrian and not talk too much about it. Paleozoic, Cambrian, Ordovician, Silurian, Devonian, Mississippian and Pennsylvanian are together called the Carboniferous, and then Permian. That's a lot to keep track of. COSDCP. I'm not sure how to make that simple for the periods of the Paleozoic era. We'll go through them a little bit. Mesozoic era has 3 periods: Triassic, Jurassic, Cretaceous, and that's a little easier because they're words you're probably familiar with Jurassic Park, and I don't know, Triassic, Jurassic, Cretaceous. The end of the Cretaceous period, 65 million years ago, end of dinosaurs. Then we're into the Cenozoic era, and this is further divided into epochs. Basically, we know more about the things the closer in time they are, because the further back in time, the fewer traces remain. And so we've divided up the periods in the Cenozoic era a little bit more, and you don't need to know these epochs. Let's just stick with the periods then: Paleogene, Neogene, Quaternary, and just know that the Quaternary is the time where we are now, unless you want to call it a new period based on the fact that we're here and making changes to the planet. Okay, so back to the Precambrian here, which is all the way from 4.6 billion years ago, which is the believed start of the planet, the formation of the planet itself, about 4.6 billion years ago, up until 570 million years ago. So this is a huge time span. This is the majority of the time period that the Earth has been around, and yet on this scale it occupies just this little space down here. So in other words, this is not drawn to scale. You see that? Precambrian is much bigger than all the rest combined. So that's the thing I don't like about this table, is that you kind of get the impression that maybe it's drawn to scale. It's not drawn to scale at all. Precambrian, most of the history of the planet. And this is a very important time period, right? The cooling of the Earth to the point where a crust forms and that the water condenses out of the atmosphere, because at first it was too hot, there was no water. It was all evaporated and trapped inside the crust as well. I mean, there's still a lot of water trapped inside the Earth, deep inside the Earth, that probably will never make it out. Other than a little bit occasionally through volcanoes. The lava does have some water mixed in there. But anyway, so 4.6 billion years ago, very, very different Earth, very, very different atmosphere. During this Precambrian time, the atmosphere developed, and I talked about that a little bit in another video where I talked about the photosynthetic bacteria releasing oxygen as a byproduct, and that combined with iron in the water, and then made the iron settle out, and then it just saturated the ocean and then the atmosphere and created this oxygen-rich atmosphere that we have now, about 21% oxygen now. Anyway, so a lot of things happening in this Precambrian time period, but we're not saying too much about it. Oceans forming, continents reforming, pushing apart, pulling together, or mixing around, all the continents together, all the continents getting ripped apart. A lot of changes happening in this time period, and again, we don't have as much evidence because it's so long ago. Just go trying to look for a rock that is 4 billion years old. You're not going to find one, really. Rocks are very old, but they're not 3.5, 4 billion years old. And why is that? Because the crusts move over time and they get folded down underneath, and the rocks that were here, they get melted. And then, they're going to come up later, but they're not going to be identifiable as that very old rock. So only a couple places on Earth have very, very, very old rocks. And so we just don't know as much about them. But someplace around 3.5 billion years ago, life began, and bacteria started doing things on this planet. And so that's a big deal. And the bacteria essentially formed the atmosphere and started forming soils, and life created the conditions that was conducive for more life. And within the last 500 million years, so 500 million years ago, at the end of the Precambrian time, we start to see some other life forms, some worms and jellyfish and things like that. Okay, so now into the Paleozoic era here. So much shorter time period, 250 million years about, or 300 million years. Anyway, this Paleozoic era, and we have Cambrian, Ordovician, Silurian, Devonian, Carboniferous, Permian. And the Carboniferous is shown here as Mississippian and Pennsylvanian. That's kind of an American thing to do, because coal in Pennsylvania is newer than coal in Mississippi, and I don't know, they divided that up into two periods, but really it's just Carboniferous period. So back in the Cambrian period, we see mollusks appear and trilobites, and great trilobite diversity. Unfortunately, the trilobites died off in one of the mass extinctions. Not the one that killed the dinosaurs, an earlier one. Trilobites were really cool, and there are a lot of great trilobite fossils out there. They range in size and shape and stuff. Jawless fishes appeared. Not quite vertebrates, but close. So that's in the Cambrian period of the Paleozoic era. Ordovician period is when we do start seeing fish. Fish with bones, vertebrate, jaws, and rays and things like this. So we're really just giving little tidbits for each of these things, right? So Silurian period, plants make it to land. Plants on land before animals on land. Should have mentioned that fungi conquered the land first. Fungi have dominated the land a couple of times in history, but the fungi made it first, then the land plants with mosses were the first ones, mosses and algae coming out onto land. And in the Devonian period, we see insects, so plants first and then insects, and the plants that we know today have very much co-evolved with insects. Every plant, has insect predators and insect pollinators and things like that. They interact closely with insects, but the first plants didn't interact with insects at all because there were no insects yet. But in this Devonian period, we're starting to see amphibians and insects. So here we are in the Devonian period. Okay, so we just gave some little tidbits of these periods. Carboniferous period, this is the one that's divided into the Pennsylvania and Mississippian. That's just called Carboniferous. And basically Carboniferous was named because of all the carbon, all the coal in the ground. Because this was the first layer that geologists gave a name to, really, was the Carboniferous period, because they were interested in England in extracting coal, because they'd chopped down pretty much all their trees. And I think it was King Charles said, no more chopping down trees. We need every tree that grows to be able to grow big so we can use them in our navy. And so people couldn't gather firewood anymore. Coal became a very important thing for heating and cooking and manufacturing and melting iron and things. So they found this Carboniferous layer where they could get the coal. And during this time period, this is the whole origin of reptiles. First seed plants were in this period. This is a long period, 570 million years ago to 240. Well, we're still in the Paleozoic era. Sorry. This period, I don't have the years for that period. We're getting more recent. Okay, we don't have dinosaurs yet. We have seed plants, but not flowering plants. Seed plants being the conifers, the pine trees. Let's just leave it at the pine trees as the example. These are naked seeds. They don't have a flower. They don't have a fruit. And an interesting side note: dinosaurs aren't yet, but they're coming. And dinosaurs were before the flowering plants. So dinosaurs never saw flowers. They never ate flowers. They never had fruit to eat, oddly enough. Okay, Permian period. This is Permian period. Turtles, crocodiles, mammals, flowering plants. We're starting to see more diversity of vertebrates. And this is putting it right up to 66 million years ago, and it says first flowering plants. Well, okay, maybe the very first ones were there at the time of the dinosaurs. This Mesozoic era. Yeah, this puts us, that's through the time of the dinosaurs. This is the age of reptiles, really, the Mesozoic era. Hopefully I'm not losing track of myself here. Mesozoic era is after the Paleozoic era. Okay, so Paleozoic era ended 245 million years ago at the Permian period. Okay, and I guess we didn't really say anything about the Permian period. Okay, so then Mesozoic era, which is going to have the Triassic, Jurassic, and Cretaceous periods. Mesozoic era starts at the 245 million years ago, goes up until extinction of the dinosaurs, basically. So it's not till the end of this that we start seeing the flowering plants. Okay, so Triassic period, dinosaurs are developing. Jurassic period, yay, dinosaurs. Cretaceous period, dinosaurs extinct. That's an oversimplification. And you know, your 7-year-olds will correct you if you say, oh, dinosaurs developed in Triassic period and they flourished in the Jurassic and then they went extinct in Cretaceous. It's a lot more complex than that. And it depends on how you want to define dinosaur and things like that. But we'll just say the whole Mesozoic era, that's the reign of the dinosaurs. And that's a good long reign, almost 200 million years. Almost 200 million years that the reptiles were ruling the planet. And so you have to think the last 65 million years is when mammals took over that role. And so 65 million years compared to 200 million years, well, 180 or whatever. The dinosaurs, well, the reptiles definitely had a much longer reign on the Earth as the dominant group. And of the 65 million years that mammals have come to dominance, we're not even a million years, are we? We're just a tiny little speck here. So tertiary period, Cenozoic era now, new era. So age of mammals, basically. And 2 periods, tertiary and quaternary. It's not just mammals, birds, insects, mammals, flowering plants, the world that we are more familiar with today. And there's still, you can still look for fossils of all these things. 66 million years ago, that's still a long time ago. So we still have lots of fossil hunting going on for looking at the evolution of mammals and the evolution of birds and how did plants look like 30 million years ago or whatever? What was the climate like 30 million years ago? And the end of this period, the tertiary period, the ancestors of humans appeared. And so the quaternary period is the last 1.6 million years, and you can say, oh, this is the age of humans, but modern humans that we like to think of as Homo sapiens, that's maybe 200,000 years. So nothing on the time scale of a billion, right? So very, very recent. And yeah, that puts us, though, the last 1.6 million years of the Earth's history. That's still a long time. 1.6 million years is the quaternary period. A lot has happened in that time. There have been many ice ages and interglacial periods and continental shifting, and there's still a lot that has happened. Diversification of mammals still going on. A little bit about the Earth now, just as a planet, and not talking about the biological. It's not perfectly round, but it's almost perfectly round. I mean, 7,900 miles diameter at the equator, 7,927 at the, 7,927 at the equator, 7,900 at the poles. That's, 27-mile difference. 27 divided by 7,900. That's small percentage. It's an almost perfect sphere, and it's actually very, very smooth, which I mentioned before. 3 layers. The crust is like the shell of an egg. The mantle would be like the white of the egg, and the core would be like the yolk of an egg. And that's pretty good, except that the crust is a lot thinner relative to the whole thing than the egg shell actually is. The crust is very thin, 5 to 25 miles thick. So at the thinnest, the crust is 5 miles thick. And then we have the mantle, and then we have the core with an outer core and an inner core. And contrary to the old novel and old movie, nobody's journeyed to the center of the Earth. Nobody's even journeyed into the mantle. We haven't even drilled into the mantle. So our deepest drilling, we have not made it through the crust. We'd like to, we're trying to, just to see, what's this mantle like that we've talked so much about. So how do we know anything about this area that we've never even drilled into? Earthquakes and how the vibrations bounce off of different things. That's how we deduce what the inside is like. So we set up stations all over the world to essentially look at an earthquake is kind of like giant sound waves traveling through the Earth. So it's kind of a way to X-ray the planet. We use earthquakes. Within the crust itself, you can pound down hard and look at the sonogram basically of how that pounding is bouncing off of different layers, because it's going to react differently. It's going to reflect differently off of oil or gas or water or rock, and so you can use that. So we have ideas, good ideas and good models about the mantle and the core, but we've never actually been there. So this tiny little crust is what we live on. It contains all known life in the universe, right? Because we haven't found it anywhere else. So this tiny, little, it's like the skin of the apple, and it contains all known life in the whole universe. And it's mostly rock, about 90% granite and 10% basalt. It's covered by a thin skin of soil and water. There's quite a bit of water, but not much soil if you look at it on the scale of the whole planet. And also within the crust is everything that we've ever used to build anything, right? All the coal, the gas, the minerals, the rocks, the clay, anything that's ever been built by humans, we've taken it out of the crust, right? We cut down trees that grew in the soil on the crust. We dig up rocks and minerals and gas and oil. That's everything. Everything you've ever seen has been on the crust. Well, I guess you can look up to the stars. That's not the crust. Okay. The crust is thin, it's brittle, it cracks. Now again, we're talking geologic time period, and continents do move slowly, but they're moving, and they crunch into each other, and the plates crunch up against each other and make mountain ranges, and they pull apart from each other, and there are volcanoes poking out and earthquakes happening all the time. So you know, the mantle is a little more plastic, a little more movable. It's not liquid. It's thought that the outer core is liquid, you know, a hot magma, but about 90 elements in our crust, but 5 of them are more common than everything else: oxygen, silicon, aluminum, iron, and calcium. Mostly things combined with oxygen. So silicon dioxide, 1 silicon, 2 oxygens, they stick together. That's what sand is made out of. That's what granite is mostly made out of. That's what glass is mostly made out of. We've taken the sand and melted it down. That's what opals are mostly made out of. So silicon dioxide is a big part of what the planet is, right? That's a huge part. And aluminum will form compounds with oxygen, iron with oxygen, right? Rust, basically, iron oxides, calcium, calcium carbonates, calcium oxides, calcium hydroxides. Anyway, those are the big 5, but obviously there are a lot more that we care about. We find all of them in the crust. All the elements that we've ever dug up come from the crust. The mantle, 1,800 miles thick. 1,800 miles thick, and we've not even gotten through 5 miles of the crust. So who knows? It could be filled with all sorts of good and useful and interesting stuff, but 5 miles down is a long ways to go. We've never made it, not even with a drill. Once we get down there, it's also extremely hot, which is another reason we can't just go visit, right? So 1,600 degrees. I built an oven in my backyard, a mud brick oven thing, a mud oven, and I can get it up over 1,000 degrees, but at that temperature, if I throw a pizza into it, it bursts into flames. So you're not going to drive down there in some special submarine when it's 1,600 degrees. And as you get further in, the temperature's just going up, 4,000 degrees. Basically, our planet hasn't cooled all that much. It's still really hot. It's just cool on the very outside. And that's kind of crazy. So we think that the mantle is composed of rocks that are heavier than the crust. They're certainly denser, getting squashed together by gravity. And they are solid, but that pressure, when it gets released, it causes them to liquefy into a hot magma. So if you get a crack in the mantle, then a crack in the crust, then the solid mantle might seep through as more of a liquid. So, it's not a magma all by itself. Probably, we think it's probably pretty solid, but anywhere that you release the pressure, it kind of turns to liquid, and that's a little hard to think about, but the pressure is keeping it solid, and less pressure turning to liquid. States of matter, go back to the idea of states of matter, gas, liquid, solid. Part of what that is the amount of pressure. Okay, so the core itself, another 1,400 miles thick, and mostly melted iron and nickel. So it's not like we're going to run out of iron. We still have a lot of iron in our crust, and not that we can get to the iron in the core, but by golly, we have plenty of it. We mentioned before that the core is what makes the Earth a big magnet. Iron is a magnetic material. The inner core is liquid, and it's spinning, and it makes a big giant magnet. which is weird. And the inner core is 800 miles thick. The outer core is 1,400 miles. And so this solid iron and nickel heated up to about 9,000 degrees Fahrenheit, as best as we can tell. Sedimentary rocks. Okay, now we're talking about types of rocks on the Earth's crust. So we're back up to the crust, back up to what we're more familiar with. And sedimentary, it's sediment that falls down, and then more falls on top of it, and more falls on top of it, more falls on top of it. It's these layers that form, they accumulate, and then over time they just kind of get glued together because of all the pressure or chemicals that kind of glue them together. And there are different types of sedimentary rock. Clastic sedimentary rock is things like sand and gravel or silt and clay that get smashed together. I don't know what the word clastic means, but clastic sounds almost like classic. And a classic sedimentary rock would be sand and gravel and stuff like that. Biological sedimentary rock, that one makes sense. It comes from biology, comes from living things. Plant stuff, animal stuff cemented together. Might be a bunch of marine shells like the White Cliffs of Dover in England. Could be microscopic marine shells, could be from corals and diatoms and things. But, you know, shells cemented together. Coal. I wanted to take just a minute to talk about coal, because it doesn't look like it comes from a plant or an animal. Here's some people from not that long ago, but long ago, gathering peat in a bog in England or Ireland or Holland or something. One of these northern countries that has soggy, flat, low land that gets a lot of growth, and it's wet a lot of the times. Things don't decay normally there. They don't decay in the same way. It's not exposed to oxygen. It's a bit acidic under these bogs, and it accumulates a lot of organic matter, and new stuff keeps growing and pushing the old stuff down, and people harvested this. Remember I told you that England ran out of trees, and the king said no more cutting down trees, and coal became a big deal. Well, not everybody can afford coal, but you can go gather peat. And peat, when you dry it out, it's all wet and soggy, but when you dry it out, it can be burned. Look at that. It's kind of like old dead logs of grass and stuff. And it's just marshes that get squished down over time. So it's organic matter. Well, if peat gets squished down and down and down and down and down, longer time period, more pressure, more time, more chemical interactions, it's going to turn into coal. So here's lignite. This is called brown coal. It's about 2 million years old to 65 million years old. And this isn't your typical coal. It's not used a lot. It has some problems. It lets out gases. It can spontaneously combust. It's difficult to transport. It breaks apart. And anyway, so it's not used a lot. Sometimes it's used to run a power plant, but you just can't transport it a long way. So you can put the power plant right near the source of this brown coal, this lignite. So here's some pictures of a lignite mine, and the nice thing about lignite is that it's close to the surface, and that you can just scrape it up, put it on this conveyor belt. It's easy to get because look, up here's the surface. We have maybe some layers of peat and dirt, and then lignite all the way down here. I threw in a piece of Roman artwork, an old piece of Roman artwork carved out of lignite. It's a bit brittle. It's not easy to carve details without breaking it. I thought it was kind of cool. If you take lignite and streak it across a piece of unglazed ceramic, it will leave a brown streak. It's pretty soft. The lignite that's used for carving specifically came from trees. It's basically carbonized trees, so not swampy grasses. This is a little harder. Keep going down, keep getting more pressure, keep getting more time. So now 100 to 300 million years of pressure, and now you've got your coal that this bituminous coal coal that you see more so. And here are a bunch of kids working in coal mines in the 1800s. Massive employment of children because they wanted to sort the impurities out of the coal, because there's a lot of stuff mixed in with the coal. And these kids were coal breakers. They were, their job was to get out the stuff that wasn't coal, get the nicer pieces, break them up into the right sizes. This was to fuel the Industrial Revolution, using coal to smelt iron and things like that. More time, or the right conditions, higher pressure, the coal kind of getting pushed under, it gets changed, it metamorphoses. So it changes into anthracite coal. This coal is highly desirable, but also quite rare. And so most coal that's used is this bituminous coal. Anyway, you don't need to know all these details about coal. That's not going to be on the test. What might be on the test would be that it's a type of sedimentary rock. It's a biological sedimentary rock. Coal is. And by the way, if you just keep squishing this down or under slightly different conditions, you'll end up with oil instead of coal. And as this coal changes over time, it may let off a bunch of gases that might get trapped, and you may end up with natural gas. So coal, oil, natural gas, we mine for them, so we call them minerals, or, well, we don't call them minerals because they're not technically minerals, but we treat them like minerals because we do mine them out of the ground. But they're all biological. They're all from ancient seabeds and ancient swamps and ancient forests, and it's a lot of energy. A gallon of gasoline is the energy equivalent of, if you took about 500 acres of land and you grew a crop of wheat on that 500 acres, and then you harvested not just the wheat kernels, but the stalks and the roots and everything, and you took all the energy from that one growing season for 500 acres and crush it for 300 million years, and ta-da, you can end up with a gallon of gas. So it took a long time and a lot of resources to make the oil and gas that we use in huge, huge quantities today. Okay, another type of sedimentary rock, chemical sedimentary rock. These are chemicals that are dissolved in water and then precipitate out. So salt, salty ocean dries up, ta-da, you have salt. Salt, you don't think of salt as being a sedimentary rock, but it is. Limestone, dissolved in water. Well, limestone is kind of biological too, because it's corals and things that I don't know, limestone, that's gonna drive me nuts. I thought of limestone more sedimentary rock composed largely of minerals calcite and aragonite, which are different crystal forms of calcium carbonate. Most limestone is composed of skeletal fragments of marine organisms such as coral, forams, and mollusks. So it is skeletal fragments of marine organisms. So it is kind of biological. But the book wants to call it chemical. Okay, we'll call it chemical. But calcite is a carbonate mineral, most stable polymorphic calcium carbonate. Calcium carbonate is what the shells are made out of. And you can't just yeah, I'm not gonna sit and learn about it right now, but okay, we'll call it chemical. It's kind of biological. Major limestone outcrops. So here's our limestone here. What can you see about this picture? There are no limestone outcrops in areas with big mountain ranges. The limestone is pretty much where there were low-lying oceans. Well, where there were oceans before. It's land now. Basically, if you raised the sea level and had these inland seas, okay, that's where you end up with limestone. because there were inland seas, and Florida was covered in water, and the water extended into much of America. Anyway, so that's the deposits of limestone. It's very common around here, and it's nice for building. I like going around town and seeing all the limestone buildings. Okay, another type of rock, igneous rock. Igneous comes from lava, volcanic, and it can be extrusive or intrusive. Extrusive is magma that reached the surface, came in contact with the air, and because it was in contact with the air, it cooled down quickly. And depending on how it cools and the conditions, you may end up with obsidian or you may end up with basalt. Remember, basalt is the crust of the earth. We said 90% granite, 10% basalt, or something close to that. So basalt's very common. It's coming out of the volcanoes. Obsidian is basically a volcanic glass. Igneous rock that didn't make it to the surface. So this is a volcanic rock that didn't make it in contact with the air, and so it cooled down below, right? It cooled below all these other layers, and it solidified slowly. And so by solidifying slowly, it had more time for the crystals to arrange themselves and form. And so you get these big coarse crystals in there. Granite, quartz, feldspar. So granite was most of the planet, and then basalt was 10% or whatever. So most of the planet is igneous rock, not sedimentary. Sandstone is sedimentary, limestone is sedimentary. What else do we have? Salt. Well, coal, looking back at sedimentary. Oh, there's another that we didn't put in here. Mind blank on the word that I'm after. Shale, is a good sedimentary rock. It's basically mud layers that got stuck together. Okay, so most of the planet's crust is igneous rock. In other words, most of the crust has gone down and got melted and come back up. Like I said, we don't have 4 billion year old rocks. We have rocks that are much newer. Metamorphic rock forms from igneous or sedimentary rock that has undergone a change in form due to extreme heat and pressure. So it doesn't matter if it was sedimentary, like limestone, that gets squished down below the crust and then gets brought back up, and it didn't melt, but it got squished really hard for a long time. Ta-da, now it's marble. Slate, I think it was the word that I just said and can't remember now. Anyway, it was another sedimentary rock that got squished down. Anthracite, mentioned coal, becomes anthracite. So metamorphic rock, it's not melted down into magma, but it's changed. It's been changed. It's undergone a change, a metamorphosis. Minerals. Okay, minerals are non-living, so coal doesn't count. Pearls don't count because pearls come from living things. Minerals are non-living. Silicate minerals are very, very common because silicon is so common. So quartz and garnet and talc, and you'll see quartz crystals a lot in granite, which is an igneous rock. And garnet and talc. Talc is a very soft mineral with lots of silicon in it. Non-metallics include sulfur, gypsum, graphite. Graphite is just carbon. Since it's carbon, it probably came from coal. If it came from coal, then it technically was from a living thing. Oh well, we'll call it just a non-metallic mineral. Sorry, I don't know a lot about these things. So, moving on. Non-metallic minerals. they don't have metallic elements. They don't have any iron. They don't have nickel, magnesium, things like that. Metallics are usually just one, we're interested in the pure metal, gold, silver, copper, uranium, things like that. We mine for that one thing. Then there are gem minerals, which have value because we like them, because we think they're pretty, and so that's why they're important to us. Diamond, okay, it's a mineral, but it's made of carbon, like graphite. It's coal that's undergone a metamorphosis, essentially. So the anthracite, squished further, heated further. I think diamonds come out of volcanic. Basically think of coal getting squished down, 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 getting to the mantle, getting melted, and then coming back up through a volcano. So if it undergoes all that transformation, then ta-da, diamond. Topaz, I'm not sure how it gets there. Opal's basically really pretty sand. The sand crystals have arranged themselves in really nice ways. Topaz is probably, nothing too exotic itself. These minerals, it's not that they're made out of really rare atoms. It's just that the atoms have arranged themselves into crystals in a way that doesn't happen very often. So it's the arrangement of the atoms that make them valuable. And there are lots of ways that we can describe minerals, and there are different tests that they do. So color, okay, well, what color is it? Streak test, I mentioned with that brown coal that you could streak it on a non-glazed porcelain tile and it would streak brown. Well, okay. Does it, if it's hard enough, it's not going to leave a color streak. But if it's soft enough, it'll leave a color. Hardness test, basically, how hard is it? Okay, so there are different numbers. Talc, which is very, very soft, and you can rub talc off with your fingers. That's given a 1. Gypsum, you can scratch it and break it with your fingernails. Calcite, you're going to need to use like a copper coin. Fluorite, apatite. Don't worry about the names of these things, but basically 1 is really soft, 10 is diamond. Diamond, very, very hard. Brief story, there was a mine in West Australia. I think they were mining nickel. They bought a conveyor belt, big mining conveyor belt from Germany, and it wore out very quickly. And they wanted a refund, and the German engineers came over and they analyzed the soil carefully, and they saw diamond dust, and the conveyor belt was wearing out because it was getting cut by these tiny little diamonds. And anyway, the German company was smart, and they said, hey, we're going to buy your mine if you'd like to sell your mine. And nickel mine's not worth that much, we'll give you a good price. Anyway, they bought the mine, and it's now the world's largest industrial diamond mine. Industrial diamonds are very small, but they're useful for diamond-coated saw blades or things like that. Okay, so diamond is very, very hard. And quartz is hard. Think of granite countertops. That's a 7. It's really hard. You're not going to scratch it very easily. Now, some people will say, well, maybe I scratched my granite countertop. Well, there's probably a coating on top of it. You probably didn't scratch the rocks. Other tests, the luster, is it dull, is it shiny, is it glassy, the crystal form that it takes, is it a cube, is it a pyramid, a square, is it magnetic, just different ways to describe it. People who are into gemstones, they really go crazy on the descriptions. They love to talk about them. Okay, we mentioned the Earth's always changing, that it looks different today than it did 500 million years ago. It'll look different in another 500 million years. Actually, it looks a lot different now than it did 20 years ago, if you want to talk about it in depressing terms of how we've taken down so many forests and things. 200 years ago, the last 200 years, we've undergone tremendous changes to the surface of the planet. But on the other hand, great big tractor, digging up stuff. we're doing microsurgery on the face of the planet. You know, we moving stuff around. We're barely scraping it, to be honest. And we can use our heavy equipment and our brains for doing things other than destruction. You know, we can say, hey, let's work with nature and create some processes to heal the planet. And there's some really simple things we could do with earth-moving equipment and shaping the land in a way that would like catch the water and slow it down and encourage life and build water systems for living things. Anyway, we can do that if we want. So our little crust kind of floating, moving around, and it's and the whole crust is on different plates, and these plates shift around very slowly. They bump into each other, they crush each other, and the movements of the plates are picked up by seismometers, right? Those are earthquakes. And we have about 15 plates: North American plate, Pacific plate, Cocos plate, Nazca plate, Antarctic plate, South American plate, Arabian plate, African plate, Scotia plate, Antarctic plate, Indian Australian plate, Caroline plate, Phil, I don't know what Phil plate is, it's short for something, Eurasian plate, Pacific plate. Anyway, they all move around. And wherever the plates are pushing against each other, earthquake zone or volcanic zone, so right through California, San Andreas fault, big fault zone there. It goes down through Mexico, all along the coast of South America, over here, Pacific plate, ring, Pacific plate. Got all kinds of volcanoes happening in Japan. This Pacific plate, these little red spiky things are probably for where volcanoes are happening. Because the Pacific plate is called a ring of fire. There's lots of volcanoes happening there. So excitement happens where the plates converge. And so things might lift up. Earthquakes can cause shifting of plates. We're going to look at 3 ways that the plates can interact. So when they're coming to each other, when they converge and push, one's going to push over the other. Okay, and it's there's all this pressure, and it's when things slip that you get an earthquake. When there's you get the pressure, and something slips and you get an earthquake. And so what happens? Well, things get pushed down, and other things get pushed up, and another thing might happen, the plates might get pulled apart. And when they do that, they're creating a space here where the magma from the mantle can come up. So divergent movements, convergent, they're coming together, divergent, they're pulling apart, transforming when they're sliding past each other sideways. And so convergent, divergent, transform. Volcanoes form mountains. It's one of the ways mountains form. You get a little crack and up comes the magma. It can be really exciting, can be devastating. Mount St. Helens, Iceland, Hawaiian Islands, they're all formed from volcanoes. If you look at the Hawaiian Islands, basically what's happening is here's this place where there's a crack and volcanoes are happening, so forms an island. Well, then the plate that the Hawaiian Islands are on, the Pacific plate, it shifts, and so now this island's over here, and now I've got another island, and shift, and another island, shift, and so you get the string of islands for the Hawaiian Islands. And the most recent one is the biggest because they get worn down over time. So you have a big island and smaller, 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 basically. And there's another one forming, and it's still a ways below the surface of the ocean, but it'll eventually get up there, and there will be a new Hawaiian island sometime in the next 400,000 years. Okay, mountains may get folded, convergence, block fault mountains where one just pops up, and then the volcanic mountains we talked about that as a force. Mount Everest is higher this year than it was last year because it's still getting pushed up. The Himalayan mountains are still getting pushed up. Now, not by much, but it's taller. Okay, and just as things are getting pushed up, they're also getting broken down. And there's weathering processes. There's water seeps into cracks, it freezes, which expands, and then it thaws, and it freezes, and it goes, and it cracks things open and breaks rocks off. Plant roots get down in there, and they crack it open further. It doesn't seem like a big deal, but you do that for 10,000 years, you're going to wear that sucker down. And so that's just the mechanical weathering process. Plus there's the chemical weathering process. Different chemicals might combine with the rock. Living things decomposing might become acidic, and that's going to combine with the limestone to wear it away. Acid washes it away. The weather, the acid rain, or just the water itself can chemically react with rocks and wear it down further. Erosion, wind, water carrying away little bits continuously. So this idea of uniformitarianism, little bit getting carried away. Glaciers, a river, but what about a river of ice? A big, slow river, and you get these valleys, these glacial valleys. There used to be a glacier here. Where did it go? Well, the climate changed. So, there are times of periods of glaciation that just carve big, wide valleys, and that's different than a valley carved by a river. Okay, soil formation, man, I love soil. I told you I could talk for an hour about soil, but I can't talk for an hour about soil because I've almost talked about an hour about everything else. But this topsoil, is very little topsoil, is very critically important. And the Midwest of the United States, historically had very deep topsoil, which was the base for much of the riches of our country. And it's not just dirt. It's all the life that's in there, all the bacteria, all the breaking down of the plant matter and the dead animals, and it's mostly plant stuff, but basically getting carbon in there, fungal networks, and it just holds a lot more water than it would otherwise if it didn't have life. And also the fungi and the bacteria can help the plants extract minerals from rocks. A fungus can essentially eat rock. It can start to dissolve the rock with its own acids. The plant can't do that, but the fungus and the plant can interact, and the plant can feed the fungus sugars, and the fungus can dissolve rock and give the plant minerals, and everybody's happy. So soil is a really pretty complex interaction between different living things interacting with the non-living, with the minerals. And then you get down into the subsoil, and your organic matter is just not nearly as much, and it's more compact, and maybe it's rocks, maybe it's clay, but you don't have as much organic matter, the humus. Okay, let's end there, and good luck on your test. I wish you well. Bye-bye.